Hi everybody, this is our lecture on section 2.4 on arc length and surface area. Okay, so the first problem is, given a function y equals f of x on some continuous function, y equals f of x on the interval from a to b, what is the length of that curve? Okay, so whereas before, and again, we're going to set up an integral to calculate this. We're going to set up an integral to calculate this, right? I mean, we've used integrals to calculate areas in various ways. We've used integrals to calculate volumes in various ways. Now we're going to use this integral to calculate this arc length as well. Okay, so how do we do that? We start by forming an estimate in terms of a Riemann sum, and then letting n go to infinity. And then, that's the same technique as before. So start by subdividing the interval from a to b into subintervals of length delta x equal to b minus a over n. And then let xi equal a plus I delta x. So that's the first step in setting up the Riemann sum. And here it looks like this. So, oops. So let's just do just 4 subdivisions here. Now connect points fx1, fx2. So let's say it this way. Estimate the curve the length of the curve using line segments S1, S2 up to Sn, where Si is as shown. So you take these points on the curve, x1, x2, x3, x4, and connect them with straight line segments. So like that. Okay, so this is S1, S2, S3, S4. So now the length of the curve of f of x is approximately equal to the sum I equals 1 to n of length Si. Right? So the length of the curve, length of f of x for a less than or equal to x less than or equal to b is approximately equal to that right there, the sum of the lengths of these straight line segments, right? And the more segments there are, the better the estimation gets. the estimation gets better and better as n goes to infinity, right? So the actual length of f of x for a less than or equal to x less than or equal to b is equal to, no longer approximately equal to, the limit as n goes to infinity, the sum I equals 1 to n, length of si. Okay, so that's the actual length, but it's not written as a Riemann sum yet. Okay, so it's not expressible as an integral just yet. So the sum length si must now be put into transformed into the sum of some function hxi delta x. So that's the Riemann sum, right? hxi delta x for some function hxi. Okay, so let's take a look at that line segment si and see what its length is. Okay, so si is right here, and it goes between these 2 points. So that's the line segment si, and then here's the function f of x. You know, f of x is doing whatever it is doing. And then si, maybe I'll make it red, has endpoints, right? Well, this is xi minus 1, fxi minus 1. That's the coordinates of that point right there. Let me write that a little better. So xi minus 1, fxi minus 1. So that's the x coordinate, and that's the y coordinate. And then this point has x coordinate xi and y coordinate fxi. So the length of si is given by just that old distance formula. Is equal to, right? Well, it's the distance formula. And what is the distance formula? Or the Pythagorean theorem, right? This is the distance formula, i.e. Pythagorean theorem. Right, well, the distance from here to here is the change in the x-coordinate squared plus the change in the y-coordinate squared. Right, the change in the x-coordinates and the change in the y-coordinates. Well, in here, so we don't confuse terms, the change in the x-coordinates is xi minus xi plus 1 squared. And the change in the y-coordinates is fxi minus fxi minus 1 squared. Right? Well, xi minus, no, not that. It's xi minus 1, xi minus xi minus 1. xi minus xi minus 1, so that's this minus this, squared, plus fxi minus fxi minus 1 squared. Okay, well, what's this? This is just delta x. So this is delta x, quantity squared, and this, we'll just call it delta y, where delta y, that's the change in y, is equal to fxi minus fxi minus 1. Okay, of course, for each y, it's different, but let's just leave it there just to simplify the notation a little bit, and you'll see why in a moment. All right, well, this is equal to, again, what I want to do is factor out the delta x squared. So it's 1 times, or sorry, is parentheses 1 plus delta y squared over delta x squared, and then I'll put the delta x squared over here. Now bring it outside the square root, and it becomes 1 plus, now delta y squared over delta x squared is just delta y over delta x squared, and then once I bring the delta x squared out of the square root, now I have delta x. Okay, so now that's the sort of form that we're looking for. This is your h of x, and this is your delta x. Okay, it's a little bit different than what we've seen before, but we'll see how to handle it in just a moment. All right, so the length of f of x for a less than or equal to x less than or equal to b, which was, as we said before, the limit as n goes to infinity, the sum I equals 1 to n of the length of si. But this is equal to the limit as n goes to infinity, sum I equals 1 to n, square root 1 plus delta y over delta x squared delta x. And this is an integral now, because this is our function h of x. It's just a little unclear what that is, but hold on a moment. This is the integral from a to b of the square root of 1 plus something squared dx. Right? Because that's in the standard form now for an integral. But what goes in here? What is this? This is the change in y over the change in x. Right? The change in y over the change in x. And as n goes to infinity, well, n goes to infinity also means delta x is going to 0. Right? As n goes to infinity, the delta x goes to 0. So it's the change in y over the corresponding change in y over the change in x as the change in x goes to 0. And that is exactly something that you studied in calculus last semester. It's the derivative, dy dx. Right? The corresponding change in y for the change in x. The ratio of those two things as delta x goes to 0 is the derivative, right? What was the definition of the derivative? Is the limit as x goes to a, fx minus fa over x minus a. That's the change in x, and that's the change in y. Corresponding change in y, right? That's f prime of a. That was the definition of the derivative, and that's exactly what we've got here, although in a more simplified sort of notation. So there it is. So that's the formula for arc length. So you can write it like that, or you can write it like this. It's the integral from a to b, 1 plus f prime x squared dx. If you don't like the differential notation, you could write it like that with the f prime notation. So for example, it's always nice to take an example where you know what the answer is ahead of time. If you know what the answer is ahead of time, then you can plug it into this formula and see if you get that correct answer. Right? So let's do a quarter circle. So 1/4 circle, well, so the circle of radius 1 has total length, circumference, 2 pi. Right? So a quarter circle has circumference, has length, 2 pi over 4, which is equal to pi over 2, right? All right, well, what function can you use to represent a quarter circle? All right, well, here it is. There's a quarter circle. That's 1 on the x-axis, 1 on the y-axis. Right, x squared plus y squared is equal to the radius squared. So y is equal to the positive square root 1 minus x squared. Right, for x goes from 0 to 1. All right, so that's my function. That gives me the quarter circle of radius 1. All right, let's find the derivative. dy dx is equal to, okay, this is 1 minus x squared. So y is equal to 1 minus x squared to the 1/2 power, yeah? So the derivative, dy dx, is equal to 1/2, 1 minus x squared, times minus 2x, or to the minus 1/2 power, times the derivative of the inside function, which is minus 2x. Simplifying this formula a little bit, 2 and the 1/2 cancel, so I get minus x over, right, that's negative 1/2 power. So I got x over square root 1 minus x squared, negative of x over that. So the length of the curve is equal to the integral from 0 to 1 square root 1 minus dy dx squared dx. So this is equal to the integral from 0 to 1 oops, not minus, plus, did I put minus above there? No, plus. Okay. 1 plus dy dx squared. So this is 1 plus this thing squared. Minus x over square root 1 minus x squared squared. Alright, so this is equal to the integral from 0 to 1. Not as hard as it looks. Simplifies considerably. 1 plus, well, when I square this, I just get x squared over 1 minus x squared. And now what I'm going to do, I'm going to add these together. So it's square root 1 minus x squared over 1 minus x squared. Right, like that. So it's equal to the integral from 0 to 1, and these just add up to 1. So it's integral from 0 to 1. Now the square root of a over b is, remember, square root a over square root b. In general, exponentiation distributes over multiplication and division. Addition does not exponentiation does not distribute over addition and subtraction, but it does over division and multiplication, like this. So this is just square root of 1, which is 1, over square root 1 minus x squared dx. Antiderivative, that's arc sine. That's the derivative of arc sine x. Right? Just classic inverse trigonometric derivative or antiderivative from 0 to 1. Well, arc sine of 1 minus arc sine of 0. Arc sine of 1 is pi over 2. And arc sine of 0 is 0. So there it is. And that's the answer we were looking for. Okay? So that's a derivation, that used this arc length formula, but we knew what the answer was ahead of time, so it's a very nice illustration of how this works. Let's take another example. Now, in general, there's precious few functions you can actually plug into this arc length formula and actually be able to solve it precisely. It's just a kind of an ugly formula, and there's just not too many functions that you plug in here that you'll actually be able to get an answer. But here's one where you can. So y equals x. Oh, so this is 2.4, number 176. So you can give this example a go on your own. The function is, so find the length of y equals x to the third over 3 plus 1 over 4x for 1/2 less than or equal to x less than or equal to, or no, for 1 less than or equal to x less than or equal to 3. Okay? I mean, I'm not even going to graph it. It's some just sort of oddball function. What's special about it is that you'll actually be able to do the calculation, although it's done in sort of a uncommon way. You might not see it off the top of the bat. But I'll show it to you just so you can see this kind of function and how it works. So first thing we need, is the derivative, dy dx. So the derivative here is just x squared, right? So this is x to the negative 1. So the derivative is negative x to the negative 2. Right? Derivative with respect to x of x to the minus 1 is minus x to the minus 2 times a quarter. Right? So this is minus 1 over 4x squared. So the length is equal to the integral from 1 to 3 square root 1 plus dy dx squared dx. So integral from 1 to 3. Okay, 1 plus. Now we're going to stick this guy inside there. Okay? So x squared minus 1 over 4x squared squared. Let's evaluate that square. So it's 1 plus x to the 4th. Now minus twice the product of these two things. So x squared times 1 over 4x squared, their product is just 1/4. Right? The product of this and this is just 1/4. Times 2 is 1/2. So it's minus 1/2 plus 1 over 16x to the 4th dx. 1 minus 1/2 is plus 1/2. Just combining those two terms. So this becomes plus 1/2. Just like that. Okay? Now, what happens is that before, right, this squared, x squared minus 1 over 4x squared is equal to this. X squared minus 1 over 4x squared is equal to this. All right, where this is x to the 4th minus 1/2 plus 1 over 16x to the 4th. This is x to the 4th plus 1/2 plus 1 over 16x to the 4th. Right, so that just equals x squared plus 1 over 4x squared squared. And so we're taking the square root of something squared. Because x is positive, x goes from 1 to 3. So because x is positive, these things are both positive. So the square root of a positive number squared is that positive number back. dx. Antiderivative is x to the 3rd over 3. And then minus 1 over 4x. All right, so plus, I'm sorry. No, minus. X to the 3rd minus 1 over 4x. So we started with the function, What did I do? That's plus. Yeah, plus became minus. We started with the function y equals x to the third over 3 plus 1 over 4x. And then we plugged it into that formula, and we ended up with this antiderivative. X to the third minus 1 over 4x. So there's, precious few functions that actually do that, but there's one of them. So evaluated from 1 to 3. So this is 27 over 3 is 9 minus 1/12. Evaluated at 1, you get 1/3 minus 1/4. So this is 9. So 1/3 minus 1/4 is 1/12. Right? Yes. So, oops. So that's minus 1/6. So 53 over 6 units long is the curve. I mean, whatever that curve looks like, I actually don't know. But, it's just a curve that's chosen because you can actually plug it into that arc length formula and get an antiderivative. Okay. So there's a couple examples. Let's go on to surface area. So before we get into that, I want to. So there's one sort of technical aspect to this surface area calculation. It's just geometry. So it's a type of geometry that it's a geometric formula that's kind of standard, but I mean it's less common than the others. So you probably have not seen it, and it's the tarbouche again, or the frustrum, or the dog cone, or whatever you want to call it. Okay, so three different parameters. And it's kind of amazing that the formula is as simple as it is. And you have this radius here. So you have the radius at the top, we'll call that little r. And you've got this radius on the bottom, big R. And then you have the length of this right here, L. And so the surface area of this thing, of this object, is going to be pi, big radius plus little radius times L. It's pretty amazing that it comes out to be as simple as that. Deriving that formula, deriving the surface area of the cone is actually, something we could do, but it'll take a while. I don't want to get into that. And they don't actually do it in the book, but I could show you that sometime if you wanted to, how to do the surface area of an entire cone. So basically, you do the surface area of an entire cone, you get a radius and you get a length like that. And then using that, you derive what this is. But even going from here to here is kind of tricky. So it's a pretty long process. So we'll just assume this for now. Okay, so that's just some assumption. All right, so now the setup is as follows. So we have a curve y equals f of x for a less than or equal to x, less than or equal to b, and we rotate it around the x-axis, and we wish to calculate the surface area of the resulting solid. Not the volume, but the surface area of the resulting solid. So, picture going like this. Let's draw something a little simpler than usual. So that's y equals f of x. So I'm going to rotate him around the x-axis. like so. Right, and I'm going to have, this thing here. And I want to know what the surface area of the solid is. Not the volume. We did the volume in previous section. Right, I just want to know the surface area this time around. So let me erase that a little bit. Like that. All right. So we need to estimate this surface with known areas, and we're going to use these things, these doggy cones or tarbushas, tarbish. So you do like this. So now estimate the surface area using a Riemann sum. So delta x is b minus a over n, xi is a plus I delta x, and you take your curve, I'll draw you a picture. Take your curve y equals f of x, and here's a, here's b. Again, we'll just use 4 subdivisions, x1, x2, x3, x4 for a picture. Right? And then you find those points on the curve and you connect with straight lines. Alright, so this is S1, S2, S3, S4. Alright, estimate the curve with line segments as before. The curve y equals f of x with line segments as before, and then rotate those line segments around the x-axis to get cones that estimate the surface area. Around the x-axis to get cones that estimate the surface generated by rotating f of x. Right? So I'm not going to attempt to draw it. Well, let me just draw the red and leave the black out of it. Just draw the cones. So oops. There we go. Right, so I've got this line segment, this line segment, this line segment, and that line segment, and now I've got my cones. Right, so these cones, they estimate the surface area in question, and the estimate gets better and better. estimate gets better and better as you know, you use more and more thinner cones, right? So the actual surface area is the limit as n goes to infinity of those cones. All right, so as before, the surface area is equal to the limit as n goes to infinity of the sum I equals 1 to n of the area, surface area of the cones of cone xi. So here's the cone at x1, the cone at x2, cone at x3, cone at x4, right? Of the cone at xi. Okay, well, what is the surface area of the cone at xi? Well, go back to that formula for the surface area of these, you know, truncated, these chopped off cones. Right? It's pi times the sum of the radii times the length. So it's kind of like a trapezoid, right? I mean, like the area of a trapezoid is the base 1 plus base 2 over a half times the height. So it's kind of reminiscent of that. So you have radius 1 plus radius 2 times pi times the length of this side. So it's not done in terms of height. You know, often these things are done in terms of height, but here this is done in terms of the length along the cone there. Which, of course, we know what that is. That came from that, you know, distance formula. Right? So that's what it is. So this is the sum I equals 1 to n pi. And what are the radii? It's fxi plus fxi minus 1. fxi plus fxi minus 1. So that's the two radius, right? F of x here, f of x there. Right? Times this length right here, length si. Well, notice that, right, this is fx1 plus fx0, and then fx2 plus fx1, fx3 plus fx2, fx4 plus fx3. So you're adding up the fx's in the middle twice. You add them up twice in the middle. So this is approximately equal to, when n is really large, or no, when n is large, so because it's a limit, it's the same thing. It's the limit as n goes to infinity, the sum I equals 1 to n, 2 pi fxi, length si. Because you're adding up each fxi in the middle twice. Right? For this cone, then the next cone, then the next cone, you use the radius for each guy in the middle twice. The guys at the end don't matter really. You use those once, but I mean you're letting n go to infinity, so that contribution just kind of goes away. All right. What was the length of SI? There was some expression for it way up here. Where is it? Right there. Right there. It's this. Right? That's what we had from before. Square root 1 plus change in y over change in x squared, delta x. And that allows us to put it in Riemann sum form. So, equal to the limit as n goes to infinity, sum I equals 1 to n, 2 pi fxi times that square root thing. Make it a little smaller. Get rid of that equal sign there. Bang. Right, so Well, what integral is that? It's the integral from a to b, right? I mean, I've got my h of x, hxi. It's the sum, I equals 1 to n, hxi delta x. I mean, the hx is this big complicated thing, you know, but it's still just a function of x times delta x. So hxi delta x. So that's the integral. It's the integral of h dx. Right? So what we got is 2 pi f x square root, and again, this is dy dx as the n goes to infinity. 1 plus, well, I'll do it in terms of f prime. So there it is. There's your surface area formula. How long is the video so far? Okay, 40 minutes. All right, so let's do an example. So this is the surface area when you're rotating around the x-axis. And of course, you're going to have the corresponding thing for rotating around the y-axis. And you know, notice it's a lot like the arc length formula. Right? It's got this f prime of x squared term inside there. Just you have 2 pi f of x here. All right, so let's do this one. This is not one of the examples in the book, but you know, it's one you can do. So we'll do the square root of x for 0 less than or equal to x less than or equal to 1. So rotate around the x-axis and calculate surface area. Alright, so y equals square root x, looks like that. Alright, it's the parabola opening along the x-axis rather than the y-axis. So this is 0, this is 1, 1. So, you know, we're going to rotate that guy and get this kind of shape. Paraboloid, as it's called. And we're going to find the surface area of that paraboloid. That's also something you do in Calc 3, by the way, these volume and surface area calculations, although they're done in a different way. You know, this is another way to do them. Okay. In Calculus 3, you're using multivariable calculus. In Calculus 2, you're just using single variable calculus. So, well, anyway, two different ways to tackle the same problem, but they're both done using integration. All right, so the surface area is, so right, that's 1, 0 to 1. Oh, by the way, so that's y, so what's well, dy dx? Alright, so y is equal to square root x, so dy dx is equal to 1 over 2 square root x. Alright, that's x to the 1/2. So the derivative here is 1/2 x to the negative 1/2, which can be written more compactly like that. Alright, so the surface area is the integral from 0 to 1. Alright, fx, 2 pi, fx square root 1 plus f prime x squared dx. So it's integral from 0 to 1, 2 pi square root x square root 1 plus 1 over 2 root x squared. Right, that is, that's the derivative, f prime, right there, plugged in. So this is equal to, let's pull the 2 pi out front, integral from 0 to 1, square root x times square root 1 plus 1 over 4x. Right, square root a times square root b. Square root ab is square root a square root b. exponentiation, or square roots, which is 1/2 exponent, distributes over multiplication and division. Not over addition or subtraction, but over multiplication. So this is equal to 2 pi times integral from 0 to 1 square root x times 1 plus 1 over 4x. So that's 2 pi times integral from 0 to 1 square root x plus 1/4. So I'm going to let u equal x plus 1/4. So du is dx. So this becomes 2 pi times the integral from x equals 0 to x equals 1, u to the 1/2 du. So antiderivative is 2/3 u to the 3/2 from x equals 0 to x equals 1. So that's equal to 4 pi over 3 x plus 1/4 from 0 to 1. So it's 4 pi over 3. So 5, oh, I'm sorry, I lost my exponent. To the 3/2. So 5/4 to the 3/2 minus, at 0, 1/4 to the 3/2. Whatever it is. So it's not a nice answer, but you know it's still just a number. Okay, so that's that surface area calculation for the paraboloid. Okay, actually it could factor out the 4 to the 3/2 on the bottom, but we'll just leave it at that. Okay, so that's it for this section.